100 trillion years from now, a once great civilization is fading away in the dark. In their prime, they built star systems and created a massive interstellar empire by taking apart planets and asteroids. But now, as their time runs out, all that greatness is long gone. The universe around them is dying, with the last stars flickering out. Over many, many years, the sky has turned into an everlasting night. The aging universe is sad and falling apart. So, in the dark, they're waiting for the end. A long time before they knew it was coming, they understood the universe was on a path of going downhill. They carefully searched for a final place to wait forever and started their last big building project. Around a lost and lonely black hole, they made a new home using pieces of broken planets. They built a shell to cover the darkness completely. Inside this thin shell, just holding on against the pull of their savior, they lived their simple lives. The last light from dying stars fell on their final home, while the black hole gave them the power to keep going. But more than just surviving, the black hole gave them something incredible: time. No one remembered who discovered the nature of time, but the astro engineers knew that time didn't work the same everywhere. In the immense gravity of the black hole, time moved more slowly. While many years passed outside, only moments went by inside their home. So the last of the civilization watched the future unfold in front of them. But they knew they were only putting off, not stopping their end. The darkness would still close in on them forever. Of course, this story is just an idea based on science that changed our universe. It's been more than a century since Einstein's ideas shook up how we see time and space. But how do they really work? And what does it mean? Both time and space seem every day, but they hide lots of questions. Questions Einstein's ideas only begin to answer. What is space made of? Does time really exist? And will looking for their ultimate nature make things clearer? Or will space and time become even more confusing? As our solitary world traversed the cosmic expanse, its rhythmic pulse warped the very fabric of the universe around it. The civilization, in a desperate bid to stave off the inevitable, employed every effort. Yet their grasp on reality could only bend it, not break it. Behind it all is surely an idea so simple, so beautiful, that when we grasp it, in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise? How could we have been so stupid? What is space? The question seems almost meaningless. As children, we learn to describe our surroundings as up-down, left-right, back and front. We call it three-dimensional, and are free to explore each dimension. But just what is it, this universal platform on which we play out our lives? It is a question that occupied the minds of the earliest philosophers. In the 4th century BC, Plato declared that space was the nurse of becoming, a medium in which everything existed but with no qualities of its own. His student, Aristotle, agreed that an empty void was impossible, but it would be more than 2,000 years before our concept of space was born. By the coming of the 17th century, modern science was crystallizing. The processes of the universe were being codified into physical laws, and the understanding of these physical laws was evolving from myths and stories to the language of mathematics. Of course, Isaac Newton was at the forefront of this revolution, but before he enters our stage, we must first start with a boat. In 1632, Galileo published his seminal work, Dialogue Concerning the Two Chief World Systems. He was in his mid-60s by this point, and had already had multiple run-ins with the Roman Inquisition for his assertions that the Earth rotated around the Sun. So he had decided to skirt controversy and spend the intervening years quietly cementing his myriad ideas on space and the cosmos into a book. And at one point, within this book, he muses on a boat. More specifically, the life of a sailor locked below deck in a windowless cabin with plates and knives and a goldfish in a bowl on the table. A collection of birds, flies, and butterflies. Just what does the sailor experience? Tied up in port, the cabin is a picture of serenity and all is calm as the goldfish swims happily in its bowl. On the table, plates and cutlery remain in their place, and the flying creatures happily flutter about. But finding itself in rough seas, the cabin heaves and falls with the ship. Plates and cutlery are wrenched off the table. Water spills from the goldfish bowl. On calm seas with wind-filled sails, the ship would speed up. The sailor would feel this change and see things sliding off the table, but when the wind finally drops, the ship sails smoothly on the glassy sea. Inside the cabin, all would be calm, serenity returning. For the sailor, it would be as if the ship was still in port and was not moving at all. A dropped plate would fall straight to the floor, and the sailor would sit comfortably in their chair. And it was here Galileo realized something. Without a window to reveal the truth, there are no experiments the sailor could do to reveal whether the ship was moving or not. He concluded that there must be no absolute concept of being at rest in space. Instead, everyone must experience any smooth, uniform motion in the same way. All uniform motion must feel like simply being still. Galileo declared, therefore, that any uniform motion is simply relative to any other uniform motion. And with this, the first theory of relativity had been born. Galileo's sailor floats gently on their sailboat on seas near the Earth's equator, rotating at 1,600 km/h around the Earth, which in turn orbits the Sun at 67,000 km/h, which in turn orbits the Milky Way at 720,000 km/h, which in turn is traveling towards the Andromeda Galaxy at 403,000 km/h. And yet he feels nothing on his vast journey, millions of kilometers from his starting point. Unfortunately, upon publishing the book, Galileo once again fell foul of the Catholic Church and was found guilty of heresy for his heliocentric view of the cosmos. The work was banned and would not be removed from the Church's Index of Forbidden Books until 1835. Within a few decades of Galileo's downfall, two of Europe's greatest minds were arguing about the nature of space. One of them, Isaac Newton, was born in England in 1642, within a year of Galileo's death. He needs little introduction and is known now as one of the greatest thinkers of his age, perhaps one of the greatest of all time. While not forgotten, his opponent, Gottfried Leibniz, is somewhat less well known today. Born in 1646 in what is present-day Germany, he was a leading thinker of his day, writing on mathematics and philosophy. He pondered deep metaphysical questions, including one that still haunts physicists and philosophers to this day: why there is something rather than nothing. It was in the development of calculus that the two men's feud began. While Leibniz published his work first, Newton claimed that he had stolen his ideas. As president of the Royal Society at the time, Newton set up a committee to investigate the dispute. Unsurprisingly, the committee found in favor of Newton, and so this animosity carried over to their second disagreement. A simple question: what happens to a spinning bucket of water? Space, Newton declared, was a universal absolute, a rigid stage on which motion was played out, and both would exist in a universe devoid of matter to experience any motion. To argue his point, Newton asked us to think of a bucket of water. If the bucket sits at rest, the surface of the water would be flat and level, but if we spin the bucket, the water spins too and its surface becomes curved. Newton asked, just what is the water spinning with respect to? Newton claimed that the acceleration of the spin was relative to an absolute space, something separate to the object itself. Spinning a bucket in an empty universe would also curve the surface of the water. But to Leibniz, space in an empty universe, devoid of any matter, simply made no sense. In the distant future universe, around the aging black hole, our dying civilization sits and waits. For sitting and waiting is all they can do. With the passing of the stars, raw energy had become the most precious thing. To preserve what they had slowed their very existence. Every aspect was focused upon survival. As their sleepy eyes watched the ever-darkening skies, as total universal heat death crept across the cosmos, they realized that time was their ultimate enemy. You may see a cup of tea fall off a table and break into pieces on the floor, but you will never see the cup gather itself back together and jump back on the table. What is time? Like space, the nature of time occupied the minds of many ancient thinkers. In ancient Greece, Aristotle stated that time was simply the steps between before and after, whilst Hindu philosophers saw time as cyclical, from creation to destruction over 4 billion years, but its true origin remained elusive. Like space, time seems to be something obvious, something that is just present. But it is clearly a different beast. We cannot freely travel through time. Unlike space, time has a direction, a distinct past and coming future. As with space, scientists can be pragmatic and not worry about the nature of time. Coupled with a ruler, a clock completes the experimenter's toolbox. But it doesn't mean we can ignore the question. And to understand time fully, we first have to think about horses and steam engines. The coming of the Industrial Revolution presented humanity with a problem. The original engines of civilization, draft animals like horses and cattle, were relatively simple things. Understanding how much to feed them and how much to work them was easy. A certain number of bales of hay could guarantee a day's work from a well-fed animal. But what of newfangled machines, such as a steam engine? How much work can you get out of a heap of coal? This was an important question from an economic standpoint. Do you replace a horse with an engine if it is going to cost more to feed it? And it was out of this conundrum that thermodynamics was born. Many minds wrestled over the question of the ultimate efficiency of engines. Indeed, at the time of thermodynamics' inception, a typical engine only worked at 3%. In a physical steam engine, the heat of the fire is used to boil water, but some of the fire's heat just radiates into the air. Metal scrapes against metal, screeching loud and hot to the touch, both forms of energy loss. In any physical steam engine, this loss of heat as waste is inevitable. Within the mathematics of thermodynamics, perfect efficiency was found to be an illusion. Energy is always lost as heat flows from one place to another. The concentrated energy released from burning coal must be degraded as it flows through the engine, and some must be lost into the surroundings. And so a new measure was introduced to account for this increase of decay and disorder: entropy. And it is probability that dictates how this happens. As the early 20th century physicist Giorgio put it, for exactly the same reason, the room in which you sit reading this book is filled uniformly by air from wall to wall and from floor to ceiling, and it never even occurs to you that the air in the room can unexpectedly collect itself in a far corner, leaving you to suffocate in your chair. However, this horrifying event is not at all physically impossible, but only highly improbable. Gamow goes on to give the waiting time of such an event trillions upon trillions times longer than the entire age of the universe. Disorder is always statistically far more likely. Through the new laws of thermodynamics, physicists revealed an inexorable growth in entropy as the universe marches on, a future universe destined to be more disordered and decayed than today's. Not only steam engines, but whole planets, stars, galaxies, filaments, all marching from order to disorder. It was in 1862 that the grim logical endpoint of these ideas was proposed by Lord Kelvin, for whom the measurement unit was named. Although mechanical energy is indestructible, there is a universal tendency to its dissipation, which produces exhaustion of potential energy through the material universe. The result would inevitably be a state of universal rest and death, if the universe were finite and left to obey existing laws. And so, was this time? A constantly dying universe heading for inevitable heat death, and stars going out one by one in a steady march from potential energy to waste, leaving the trillion-year-old universe dark and spent? One of the great minds to occupy themselves with entropy and the arrow of time was James Clerk Maxwell, the iconic Scottish 19th century scientist. His views on thermodynamics shaped our understanding of heat and gases, and he did all this with the assistance of a demon. Maxwell understood the implications of entropy. He knew that if he mixed two gases, one hot and one cold, the result would be warm gas. And he knew that the gas would stay warm and mixed, rather than separating into two halves, with hot gas in one and cold in the other. But he wondered, what if we introduced a tiny demon who can sense each and every atom in the gas? This demon can turn around atoms, directing slow atoms to one side and fast to the other. As the temperature of a gas is a reflection of the average speed of its atoms, the demon has effectively separated the warm gas into two unequal halves, one hot and one cold. The demon seems to have broken the laws of thermodynamics. It has taken the disordered state, the warm gas, and created a more ordered state, hot and cold gas. And whilst only a thought experiment, arguments over the meaning of Maxwell's demon have raged for over 150 years. Some have stated that the demon must be expending energy to sort the gas atoms, and so total entropy will continue to rise. However, some have proposed that it is not energy that is important, but the fact that the demon uses information, namely the speeds of the atoms, to do the sorting. Linking energy, entropy, and information might seem a little strange, but over the last 3/4 of a century, this link has become stronger and stronger. And as any touch of a computer will tell you, processing information generates a lot of waste heat. But the situation is more complex than that. It is not simply the processing of information that leads to waste heat, but the forgetting of information. When we add 3 and 2, the answer is, of course, 5. But if I told you an answer was 5 and ask what two numbers are summed together, you cannot answer. In a computer, logic gates combine electronic signals to do the addition. Whilst two numbers are fed in, they are forgotten as the single answer is spat out. The calculation is irreversible, the inputs lost to the universe. And in the action of forgetting, the logic gates heat up a little. Thermodynamics therefore provides us with the ultimate limit for forgetting. Called the Landauer limit, it is the inevitable release of energy from erasing a single bit of information. And at room temperature, it is just over 1/100th of an electron volt. Proven experimentally in 2012, scientists believe that at present computer chips produce thousands of times more heat than this limit, but by 2035 they will most likely reach it, that tiny bit of waste heat, inescapably increasing the entropy of the universe. Ultimately, across the universe, it is this irreversibility of calculations that drives entropy to increase. Forgetting information is therefore an essential ingredient for defining an arrow of time. Does this mean that for yesterday and tomorrow to have meaning, we must forget? Is the existence of the future implicitly tied to our inability to remember? And it is now we can return to our lonely civilization on the brink of universal heat death in the far distant future. When all useful energy is used up and entropy is at maximum, would time even have any meaning? Fundamental physics does not yet have a definitive answer, but it is an intriguing possibility. But we have now reached a turning point. The foundations of time and space can only get us so far. And though they are useful, there is a revolution coming, a new order that will lead directly to the last days of our lonely black hole world. As we continue in our journey, we're going to have to explore new time and new space.